In the previous lectures, we had done the basic theory of measures and integration, and today we will start with the notion of product measures and integration on product measure spaces. So, to start with, we will have the notion of product sigma algebras. So, let us start with the two measurable spaces x a and y b, be measurable spaces. Then a subset of the product space x cross y, a subset E is called a measurable rectangle if it looks like A cross B, where A belongs to the sigma algebra A and B belongs to the sigma algebra B. The collection of all measurable rectangles, or just called as rectangles, will be denoted by the set R. So, the set R denotes the class of all measurable rectangles, which are subsets of the set x cross y, and each subset is of the type A cross B, where A is in the sigma algebra A and B is in the sigma algebra B. In general, we had already observed while discussing the notion of semi algebras, algebras and sigma algebras, that sets of the type A cross B, where A comes from a sigma algebra and B comes from another sigma algebra. This collection of rectangles in general need not form a sigma algebra. In fact, it does not even form, it need not even form, it need not be even a algebra. But surely, A and B are being sigma algebras, they are also semi algebras, and then we had shown that the rectangles sets of the type A cross B surely form a semi algebra. So, the set of all measurable rectangles, they surely form a semi algebra of subsets of x cross y. So, this being a semi algebra of subsets of set x cross y, and in general may not be a sigma algebra, we can generate a sigma algebra by these rectangles. The sigma algebra generated by these rectangles is denoted by A times B, and A times B here is the special symbol cross with a circle. So, A times B will denote the sigma algebra generated by the rectangles R. Let us give another characterization of these sigma algebras, the product sigma algebra, in terms of what are called the projection maps. So, let us look at the map P x, P lower x, which is defined from x cross y to x, as P x of x comma y is the first coordinate x, and similarly P y is a map from x cross y to y and is denoted by P y of x y is y, the second coordinate. So, these two maps, they are called the projection maps, the projection of x cross y onto x and onto y. So, the claim is that in case we give x cross y the product sigma algebra, then these are measurable maps. So, let us prove this. So, x cross y to y, on x we have got sigma algebra A, on B we have got the sigma algebra B, on y we have got the sigma algebra. So, let us okay. So, let us look at A. So, x cross y to x. So, here we have got the product sigma algebra A times B on x cross y, and on x we have got the sigma algebra A, and P x is the map defined on x cross y to x, and it is defined as P x x comma y is equal to the first coordinate x for every x comma y belonging to x cross y. So, our claim is that this P x is a measurable map when we give the product sigma algebra on x cross y. So, P x is A times B measurable. So, to show that, what we have to show is the following. That means, for every set A belonging to the algebra A, if we look at P x inverse of A, then that belongs to the sigma algebra, product sigma algebra A cross B. So, that is what we have to show. So, let us calculate. So, we note that P x inverse of A, so it is all x comma y belonging to x cross y such that x belongs to A. So, that is the meaning of the set P x inverse of A, but that is same as x belongs to A and y is independent. So, this is A cross y, just the set A cross y, and A belongs to the sigma algebra A and the set y belongs to the sigma algebra B. So, this is actually a rectangle. So, this belongs to P x inverse of A actually belongs to a rectangle. So, which is which generates the sigma algebra A times B. So, that shows that the inverse image of every set in the sigma algebra A under P x is in the sigma algebra, product sigma algebra A cross B. So, that shows that P x inverse, that means P x is A times B measurable set, measurable map. So, P x is A times B measurable, and similarly we can show that the P y. So, P y, which is a map from x cross y to y, where P x P y of x comma y is y for every x comma y belonging to x cross y. So, then for every set B in the sigma algebra on y, that is B, if we calculate P y inverse of B, that is all x comma y such that all x comma y such that P y. So, y belongs to B, and that is same as x cross B, and which is a rectangle. So, which is a rectangle and hence is in the sigma algebra A times B. So, for every set in the sigma algebra B, P y inverse of B is in the product sigma algebra A times B. So, that implies that P y is A times B measurable. So, this is a measurable map. So, what we are saying is that the product sigma algebra A cross B, the product sigma algebra A cross B is a sigma algebra on the product space x cross y, which makes both the projection maps P x and P y measurable. So, that is the property we have just now proved. In fact, something more can be said. One can even show. So, this is the proof. We just let us go through the proof again. If A belongs to A and B belongs to B, then P x inverse of A is just A cross y, which is a rectangle, and P y inverse of B is again a rectangle, and hence they both belong to the product sigma algebra, and hence P x and P y are measurable. So, what we want to show actually is that A cross B on x cross y is the smallest sigma algebra of subsets of x cross y, such that the earlier property holds, namely this is the smallest sigma algebra of subsets of x cross y, such that P x and P y are both measurable. So, let us look at a proof of that. So, let us assume, so let S be a sigma algebra of subsets of x cross y such that both P x and P y from x cross y. So, P x will be, so let us write P x will be in x, and P y which will be x cross y to y are, so that both these maps are measurable. We want to show that A times B, A times B is also a sigma algebra of x cross y with respect to which both P x and P y are measurable, and we want to show this is the smallest. That means, if S is any other sigma algebra, so that P x and P y are measurable, we want to show that it must be including A times B. So, A times B is inside S. So, let us to prove this, let us take a set. So, note, if you take a rectangle, so if you take a set A cross B, which is a rectangle, then this rectangle A cross B, I can write it as A cross B can be written as A cross y intersection with x cross B. So, this is a simple set theoretic fact that A cross B, I can write it as A cross y intersection with x cross B, because the first component A cross x will give me A, and the second component y intersection B will give me B. And this set A cross y, just now we saw it is nothing but P x inverse of A, and the second set x cross B is P y inverse of the set B. So, the set A times B, A cross B can be written as P x inverse of A intersection with P y inverse of B. And we are given that the sigma algebra S has the property that both P x and P y are measurable. So, as a consequence of this, for every set A in the sigma algebra A, P x inverse A will belongs to the sigma algebra S, and P y inverse also belongs to P y inverse of B also belongs to S, because P x and P y are both measurable. So, this belongs to S. So, what we have shown is that if S is a sigma algebra with respect to which both P x and P y are measurable, then S must include all rectangles. So, our analysis shows, so implies that all rectangles are inside the sigma algebra S, and we wanted to show that the product sigma algebra is inside S. So, it is enough to show that S is a sigma algebra. So, let us claim and try to prove that S is a sigma algebra. S is a sigma algebra. So, what we have to show that first, if we look at empty set, then I can write empty set as equal to either P x inverse of empty set or P y inverse, and hence this belongs to and so P we want to show that S is a sigma algebra. So, that means S is already given to be a sigma algebra, we do not have to prove this. So, what we have shown, all the rectangles are inside S and S is a sigma algebra. So, that implies that A times B is also inside S. So, A times B is the smallest sigma algebra with respect to which both the projection maps are measurable. So, let us go through the proof again. So, if S is any other sigma algebra of subsets of x cross y, say that both P x and P y are measurable, in that case we want to show that S, this is a typo, we should show that S includes A times B. So, let us take a set A in A and B in B, then A cross y is P x inverse of A as just now observed, and x cross B is P y inverse of B, and both belong to S because P x and P y are measurable. So, A cross y and x cross B are both sets in the sigma algebra S. So, their intersection must belong to the sigma algebra, that means A times B, A cross, which is A cross y intersection with x cross B belongs. So, all the rectangles are inside S and S is a sigma algebra. So, all the sets in the product sigma algebra, that is the smallest sigma algebra including rectangles, must also come inside. So, that shows that the product sigma algebra is inside S. So, product sigma algebra is the smallest sigma algebra of subsets of x cross y with respect to which both the maps P x and P y are measurable. Okay. Let us look at some more properties of generating sigma algebras on product spaces. So, let us look at this problem. Let us look at two sets x and y, of course, non-empty sets, and let us look at two families of subsets of x and y. So, C is a family of subsets of x and D is a family of subsets of y. Then we can form rectangles by elements of these families. So, let us denote C times D to be the collection of all sets of the type C cross D, where C is in the collection C and D is in the collection D. And now, so this is a collection of subsets of x cross y, and we can generate a sigma algebra out of it. So, on the other hand, we can first generate a sigma algebra out of the collection C and then generate the sigma algebra out of the collection D. So, there are two ways of generating sigma algebras of subsets of x cross y. The first is look at C cross D, that is a collection of subsets of x cross y, and look at the sigma algebra of subsets of x cross y generated by them. On the other hand, look at the sigma algebra generated by C. So, call it as S of C, that is a sigma algebra of subsets of x, and generate the sigma algebra by the collection D. So, call that as S of D, and then take the rectangles generated by these two sigma algebras. So, that is S C cross S of D. So, the question is, are these two things equal? So, let us observe that since C cross D is already contained in S of C cross D, so the sigma algebra generated by them will be inside it. So, the first observation is that in general S of C cross D will be inside S of C cross S of D. So, that follows from the fact. So, this follows from the fact. So, we want to. So, we have got a set x, we have got a set y, we have a collection of subsets of x, we have a collection of subsets of y, that is D, and we have a so we form a collection of subsets of x cross y, that is C cross D. So, we can generate the sigma algebra by C, we can generate the sigma algebra by D, and also we can generate the sigma algebra by C cross D. So, the question we are analyzing is S of C cross S of D equal to S of C cross D. So, the first observation is we are going to note is the following. So, C is contained in S of. So, the question is whether this product is equal to this. So, the question first observe that C is subset of S of C and D is contained in S of D. So, C cross D is going to be a subset of S of C cross S of D, and we can generate the sigma algebra by these rectangles. So, that will be a subset of S of C times S of D. Okay. So, C cross D is always in the product sigma algebra, product of the sigma algebras S of C times S of D, and so that implies the smallest one, that is the sigma algebra generated by C times D must be inside S of C times S of D. So, this is always true that the sigma algebra. So, first take the product of the families C and D and generate the sigma algebra out of it, then that is always a subset of. First generate the sigma algebras S of C and S of D, and then they take their product S of C cross S of D. So, the question is the other way around equality true, and we will show by an example that in general the inequality, the other way around equality may not hold, namely that S of C times S of D may not be a subset of S of C cross D. So, for that a simple example works. So, let us take x to be any set and y to be the set consisting of 4 elements 1, 2, 3 and 4. Let us look at C, the collection which consists of just the empty set, and the collection D which consists of the empty set, the set 1 and 2 and the set 3, 4 and the whole set y. So, the collection D consists of 4 sets, the empty set, the whole space, the subset with 2 elements 1 and 2, the subsets with 2 elements 3 and 4. So, note if we generate the sigma algebra by C, that is same as the algebra generated by C. So, that will be just empty set and the whole space. So, S of C is empty set and the whole space X, and the sigma algebra generated by D is equal to D itself, because D itself is a algebra. The complement of 1 and 2, that is 3 and 4, that is here, complement of 3 and 4 in the set Y, that is here, phi and empty set and the whole space are there. So, D actually in itself is a algebra. So, the sigma algebra generated by D is equal to, because it is a finite collection. So, the sigma algebra is the algebra itself, that is equal to D. And if we look at the product, the rectangles generated by C and D. So, the first component is always going to be empty set, that means C and C cross D is just the empty set. So, the sigma algebra generated by S of the sigma algebra generated by the collection C cross D will be the empty set and the its complement, that is the whole space, that is X cross Y. So, S of C cross D consists of just 2 elements, namely empty set and the whole space X cross Y. On the other hand, if you look at S of C cross S of D, then it consists of the empty set, the whole space of course, and then it will consist of sets of the type X cross the set in Y, that is 1 cross 2, and of course, the set X cross 3 cross 3 comma 4. So, there are at least the sets empty set, the whole space, and the sets of the type X cross the 2 elements set 1 2 and X cross the 2 elements set 3 and 4. And of course, this is not going to be equal to S of C cross D. Okay. So, even S of C cross D is not equal to even the rectangles. So, it can't be actually equal to the whole of S of C times S of D also. So, in general we cannot expect that given. So, in general we cannot expect that if you take 2 classes of subsets, one of X and one of Y. So, C is a collection of subsets of X and Y is a D is a collection of subsets of Y. So, we can take the rectangles from C and D formed by taking elements from C and D. So, that is the sets denoted by C cross D, and then we generate the sigma algebra out of this collection. So, that will be the sigma algebra S of C cross D, that may not be always equal to the sigma algebra generated by C times the sigma algebra generated by D. However, we would like to find some conditions under which we can ensure these two are equal, and that is going to be our next theorem.